Hello and welcome to this video on neutral displacement in star networks. And if you've been following our previous videos, you'll have hopefully seen a star network like this. We have a star connected source connected to a star connected load. And throughout our videos, we've occasionally mentioned this fourth wire, this neutral connection here. And what we said was if a network is perfectly balanced, then we'd expect to have no current flowing through this neutral wire. And if the network is not balanced, we would expect some current to flow through this neutral wire. If you haven't watched our previous videos where we look at balanced and unbalanced star networks, I would suggest going back to review those first, but we're going to pick up where we left off really and start to look at a case where we have an unbalanced network but this neutral wire is not present. So if we imagine removing that neutral connection there, we would just have what's known as a three-wire star network. We have our three lines, but no neutral connection. And we're going to see what the effect of that is where we have an unbalanced network as an example. Before we sort of remove this neutral connection in our minds, let's just take a look to see what we mean by having this neutral connection in place and the effects that it has. So what we can see here at the source is that our star point is grounded in this case. We have 0 volts at the star point. And assuming that this conductor is a perfect conductor, it doesn't have any impedance or resistance of its own, then what that means is that by having this neutral connection in place, our star point at the load is also going to be at 0 volts because these are connected to one another. They're going to share the same potential. What I've done here is I've noted these as Vn, the neutral voltage as it were, the voltage at that neutral point of the star point. And on the load side I've noted that as Vn dash, which is also in this case 0 volts. So let's take the assumption that we're removing this neutral connection and we'll instead see something that looks like this. The problem that we have is that when we've been previously determining our voltages and our currents, they've been with reference to 0 or relative to 0, relative to ground. And that's been fine when our neutral connection has been in place. But when we remove that, we have two options as to what's possibly going to happen in a case where we have a three-wire network like this. First of all, if the network is perfectly balanced, and we've talked about balanced networks in a previous video, we know that the current at the neutral point will be 0. And given Ohm's law, V equals I times R, it means that the voltage at this neutral point is also going to be 0. So actually it doesn't make any difference. Assuming that our network is perfectly balanced, then really there's no effect of removing this neutral conductor. It wasn't current carrying anyway. There was no potential difference to begin with, and so we can assume that the voltage is consistent at the neutral point. We have 0 volts at the source and at the load. So in other words, our system's unaffected. If it's balanced, our system is unaffected by the removal of this neutral wire. If the network is not balanced, we know that there's a non-zero current that would have flowed through this neutral connection here. And that means that there is a potential difference between our star point at the load and our star point at the source. And the problem we have is, let's say we remove this neutral connection. We don't know what this voltage is. So I've marked this on here, Vn dash equals question mark. We don't know what this voltage is going to be. But what we do know in the case of an unbalanced network is that in the case where we have a three-wire network like this, and there's no neutral connection, Vn dash will not be equal to Vn. And so Vn dash becomes what is known as a displaced neutral or a floating neutral. In other words, the value of Vn dash has drifted away from its expected value of 0 because of imbalance. So what's the big problem with this? Well, in our previous examples, when we've been calculating things like phase voltages, phase currents, that kind of thing, what we've been doing, though we might not have stated it explicitly, we were making those calculations with reference to ground, with reference to 0 volts, as it would have been the case had that wire been in place. Now that we've removed that neutral connection, we don't know what we're measuring relative to. Let's say that we're measuring the voltage across Z1. We're measuring the voltage of what would have been V1 applied to that impedance Z1, but V1 relative to what? Well, it's not relative to 0, relative to ground, as it would have been on the source side over here. Rather, it's relative to Vn dash, and we don't know what Vn dash is. So we can't really work out the voltages across our phases. And because we can't work out the voltages across the phases, we can't work out the currents that flow through them either. So, in other words, we want to be able to calculate the value of what we'll call V1 dash, the voltage as it is at the load across Z1. Similarly, we want to calculate V2 dash and V3 dash, but these are all potential differences, and we would express them like this. V1 dash is equal to V1 minus Vn dash. It's the potential difference between V1 as applied relative to Vn dash, the neutral point on our load side. Similarly, V2 dash would be equal to V2 minus Vn dash, and V3 dash would be equal to V3 minus Vn dash. Now, for all of these, we run into the same problem. We don't know the value of Vn dash, and so we can't calculate these values until we know that. Fortunately, in this case, we are rescued by Millman's theorem. And Millman's theorem allows us to find the value of Vn dash. Now, Millman's theorem could be applied to all sorts of different networks and circuits, but for our purposes, we see it appear something like this. We have Vn dash is equal to V1 Y1 plus V2 Y2 plus V3 Y3 over Y1 plus Y2 plus Y3. So you'll notice that this formulation of Millman's theorem includes the parameter Y for each phase, Y1, Y2, Y3. And you might have come across Y in previous studies. It stands for admittance, and it's the inverse of impedance. In other words, Y equals 1 over Z. And the unit of admittance is Siemens. Sometimes it might be written as ohms to the minus 1, the inverse of ohms. But these all mean the same thing. So let's just take a quick side note here on how we can calculate admittance. Since the admittance is simply the inverse of impedance, it's easy to calculate if the impedance is just a simple resistance. So let's say we had Z equals 10 ohms. Well, Y we know is 1 over Z, which in this case would be 1 over 10, which would be 0.1 Siemens, or 0.1 ohms to the minus 1. The same is true if the impedance is purely reactance. Let's say that Z equals J4. Well, we have Y equals 1 over Z again. In this case, 1 over J4. And that's going to give us minus J 0.25 Siemens. Recall the identity that 1 over J is equal to minus J. And so what we have here really is the 1 over J is giving us this minus J, and the 1 over 4 is giving us 0.25. Where things get slightly more awkward, unfortunately for us, is if our impedance is a complex number which consists of both real and reactive components. And that's going to be the case in our example, unfortunately. So let's say, for example, we have Z equals 10 plus J4 ohms. So it's a complex number now. We have a real component of 10. We have an imaginary component of 4. We've got two options here. We can use the complex conjugate to work out our admittance Y, or we can convert a polar form to work out the admittance y. Let's try both of these, and you can make your own mind up as to which you prefer. So first of all, using the complex conjugate, we need to use the complex conjugate because y equals 1 over z, and we're dividing by a complex number in rectangular form, in this case, in Cartesian form. And so because we're dividing a complex, or dividing by a complex number, we need to use the complex conjugate. And recall that the complex conjugate is simply just the complex number with its the sign of the imaginary term changed. So we had 10 plus j4, the conjugate would just be 10 minus j4. And we multiply by a fraction which has the conjugate as both its denominator and its numerator, so top and bottom. So we'd see something like this. We started off with saying that y equals 1 over z, in our case 1 over 10 plus j4. And all we're doing is we're multiplying by the conjugate top and bottom, 10 minus j4 over 10 minus j4. The reason we can get away with doing this, we're just multiplying by something strange here. The reason that we're doing this is because anything over itself is equal to 1. And so really we're multiplying by 1, which doesn't change the answer. So multiplying by the complex conjugate is cheating, really. We're not actually changing the answer by multiplying by this, because we know that it's the same thing as multiplying by 1. But when we expand, as we're going to do in just a second, we'll see that it helps us find our answer despite being in Cartesian form. So let's rewrite this top and bottom, because 1 times 10 minus j4 on the top, well, we're just multiplying by 1, so the numerator at the top isn't going to change. On the bottom, let's express this as double brackets. We have 10 plus j4 multiplied by 10 minus j4. And we can expand those double brackets on the bottom. Again, I tend to use this FOIL acronym. So the first two terms in the bracket, in each bracket, the 10 and the 10, multiply to give us 100. The outside, or the outermost two terms, 10 minus j4 is going to give us minus j40. The innermost or inside terms are going to give us plus j40. And the last two terms, the last in each bracket, plus j4 multiplied by minus j4, is going to give us minus j squared 16. Recall the identity. I'll make a note at the side here. The definition of j is that it's the square root of minus 1. And so j squared is going to be minus 1. And so notice we have minus j squared. So minus j squared is minus minus 1. In other words, plus 1. And when we multiply something by plus 1, it doesn't change. So we just have plus 16 here, rather than minus j squared 16. The other thing to notice is the minus j40 and the plus j40, they'll cancel one another out. And so we're simply left with what was 100 plus 16. That's going to give us 116 as our denominator now. And we can break that into separate terms. We could say that that's equal to 10 over 116 minus j4 over 116. That's the same thing, and we could express that as a decimal as well. We end up with this 0.0862069 minus j 0.0344828. And remember, we've worked out an admittance here, y, and it's measured in Siemens S. We mentioned that we were going to try two methods. We've used the complex conjugate to find the admittance of a complex impedance. Let's also use polar form and hopefully find something that is very similar. There might be a little bit of rounding error when we're converting between polar and rectangular forms, but we'll hopefully get a reasonably accurate result. So to find the inverse of a complex number in polar form, we do two things. I'll make a note of these here. First of all, we find the inverse, or the reciprocal, of the magnitude. And secondly, we change the sign of the angle. So if we were to express that as a formula or equation, let's suppose we have a complex number in this form: z equals a at an angle of theta. It doesn't matter so much what a and theta are to begin with. But let's say we have a complex number in this form, in polar form. Then y is going to be 1 over a at an angle of minus theta. So we found the reciprocal or the inverse, 1 over the magnitude, and we've changed the sign of the angle. So if it was positive, it becomes negative. If the angle was negative to begin with, it would become positive. So let's apply this to our example of Z equals 10 plus J4 ohms. First of all, this is in rectangular form, it's not in polar form. So the very first thing we have to do is convert this to polar form. And the easiest way to do that is just using the pol function or similar on a scientific calculator. Or you can use trigonometry to convert between them. But in our case, we have Z equals 10.7703 at an angle of 21.8014 degrees. And that's in polar form. So now we know Z in polar form, we can convert it, just as we've seen above, to an admittance. It would look something like this. Y equals 1 over 10.7703 at an angle of minus 21.8014 degrees. We've changed the sign. And in our case, 1 over 10.7703 gives us 0.092848 at an angle of minus 21.81014, like we saw there. And lastly, we can convert this back to rectangular form again. You could just use the rec function on a scientific calculator, but in rectangular form, we've converted back, and now we have 0.0862072 minus J 0.0344829. Remember, it's an admittance, so it's measured in Siemens. You might notice a very small difference between this result and the result that we found using the complex conjugate, but the answers are very similar. But the complex conjugate is always going to give us a more accurate result because there's always some rounding that's going to take place when we convert to polar form and then back again. In the example that we're going to look at in this video, we are going to use polar form just to make things easy. But we should make sure that we use as many decimal places as reasonably possible in order to keep as much precision in the answer. If we start rounding to 1 or 2 decimal places, then very quickly we're going to lose a lot of accuracy as we go through the steps. So let's get back to Millman's theorem. And we were doing this to find the potential of the displaced neutral Vn dash. And we saw this formula here, v1y1 plus v2y2 plus v3y3 over y1 plus y2 plus y3. And we've talked about now admittances and how we can calculate those. So let's apply this to the same circuit that we saw in a previous video actually on unbalanced networks. But whereas last time we assumed there was a neutral wire, neutral connection, let's this time assume that there's no neutral connection. And so what we're going to see is a case where we have this displaced neutral, hopefully. So we'll use the same values as we did in a previous example. We had V1, V2 and V3, our supply phase voltages being as 240 volts at angles of 0, minus 120 and plus 120 degrees. And we had 3 impedances that were all different because we had an unbalanced network. We'll use the same impedances. We had 4 plus J2 ohms for Z1. Z2 is 3 minus J3 ohms, and Z3 is 5 plus J or 5 plus J1 ohms. So for Millman's theorem, we need to convert our 3 impedances here into 3 admittances. Let's skip the working here, but whether we use the complex conjugate or use polar form, we should end up with 3 admittances regardless, just using the methods that we've talked about. And I'll just summarize the working for each of those here. You might want to pause the video and see if you can calculate these for yourself. But here we have them in rectangular form and in polar form. So regardless of which method you've used, we should be able to get something similar. Now all that remains to do is to substitute our values into Millman's theorem. And it's probably best to use admittances in polar form in the numerator anyway, because we're going to be multiplying several things together as complex numbers. And so it's probably easier to do that in polar form, as we'll see. So even if you've worked out your results in Cartesian form using the complex conjugate, it's advisable, to be honest, to convert them anyway to polar form for this next step. You can multiply numbers together in rectangular form. It's just a bit more time consuming, and we're not going to do that in this video. But anyway, we substitute those values into our formula here, and we'll see something very big to begin with, like this. So one of the advantages of having our admittances in both rectangular and polar forms is you can see here that when I've substituted the admittances in the numerator of our equation for Millman's theorem, they're in polar form because we're going to be multiplying on the top row. And when we see them on the bottom row, y1 plus y2 plus y3, these are in rectangular form because we're going to be adding on the bottom row. And that's just for convenience sake in this particular example. It's not necessarily the only way to do it. Like I say, you can multiply numbers in rectangular form if you want to, just by expanding the brackets, but we're going to keep things fairly simple for this example, hopefully. So looking at the numerator of our example here, you can see that we have these sort of double brackets 3 times here, and these are both in polar form. And so when we multiply two numbers in polar form, we simply multiply the magnitudes of each and we add the angles of each. So we'd have 240 multiplied by 0.2236, which gives us 53.6656 in this case, and we would add 0 plus minus 26.565, and that's going to give us minus 26.565 as our angle. And the same method for each of these. So now we have 3 terms in polar form after we've multiplied each of those double brackets together. On the bottom row, all we do is we add together the real terms. We've got three complex numbers in rectangular form to add together. We're adding together the real terms, a fifth plus a sixth plus 5 over 26. And we're adding together the j terms. We've got minus j 1 over 10. We've got plus j 1 over 6. And we've got minus j 5 over 26. And I've rounded those to a decimal here, but we have something that looks like this on the bottom now once we've completed those additions. So at this stage, you'll look now and notice that we have 3 terms on the top, the numerator of this equation, that need to be added together. And unfortunately, it's much easier to add together in rectangular form. So just for the purposes of simplicity, we're going to convert again and convert these each into rectangular form, and we'll end up with something that looks like this. All I've done here is just use the rec function on a scientific calculator to convert these each into rectangular form. And again, we can add these just like we did on the bottom of the fraction before, adding the real terms, adding the imaginary terms, we get something that looks like this. And finally, we could use the complex conjugate to perform this division in rectangular form as it stands. We're going to cheat a little bit and we're going to convert them both again back to polar form. So just using the pol function on the calculator. We've converted these to look something like this now. And when we divide in polar form, we simply divide the first number, the magnitude, so 58.4939 divided by 0.559686. And we subtract the angle, so we'd have minus 35.6055 minus 2.88862. And so we get a result that looks something like this. So what we've now found is the value of our displaced neutral Vn dash. Now in a perfectly balanced system, as we said at the very beginning, this value should be 0. But in our example, we find that the voltage at the central star point is actually over 104 volts in magnitude relative to ground. So what we can see here is if a star network's neutral wire, say it was a 4-wire star network to begin with, if that neutral wire was broken or disconnected or otherwise poorly maintained, then if we have an unbalanced system, this will result in these big swings in voltage and these neutral displacements that we've sort of examined mathematically here. Okay, so now that we know the value of Vn dash, our displaced neutral voltage, we can now work out the voltage across each of our load phases, Z1, Z2 and Z3. Earlier on we called these V1 dash, V2 dash and V3 dash, and we said that these were the difference between the applied voltage V1, V2 and V3, in each case minus Vn dash. So we're calculating these relative to this new displaced neutral voltage. So let's put these into practice. We've said that V1 dash is equal to V1 minus Vn dash. Well, V1 is given to us. It was 240 at an angle of 0. It was one of the things that we said at the very beginning. But we're subtracting this displaced neutral voltage that we've just worked out. It was 104.387 at an angle of minus 38.4941. Again, we're performing a subtraction here. It's more convenient to do this in rectangular form. So here are the same values converted to rectangular form. And we can subtract, again, just subtracting the real components, subtracting the imaginary components. Watch out for double negatives here because we're minusing a minus j term here, minus j 64.974, which will become a plus because of that double negative. And in polar form as well, we'll see something like that if we wanted to convert it back into polar form as well. Here's similar working for V2. In this case, V2 dash is going to be equal to V2 minus Vn dash, and so V2 looked something like this, 240 at an angle of minus 120 degrees. We're subtracting that same Vn dash. These are all connected to the same displaced neutral point, so the Vn dash is the same for all of them. Again, we can convert to rectangular form and perform that subtraction and convert to polar form if we want to. V3 dash, exactly the same method. V3 this time at an angle of 120 degrees, minus that same displaced neutral Vn dash. Here it is in rectangular form, here it is subtracted, and here it is converted back into polar form. We've whizzed through those quite quickly just for the sake of time, but you may want to pause the video and make sure that you're happy with those calculations yourself. Now that we've calculated the voltage across each phase, these are the voltages that would be measured across each of those impedances of the load. Let's take a quick moment to notice the magnitudes of these voltages. Let's look at V3 dash in particular, because it reaches as high as 339 volts. Now remember that the supplied phase voltage, which we intended, was only 240 volts on each phase. And the displaced neutral means that the phase voltages will either be greater or smaller in magnitude than the expected voltage of 240 volts. And it may well be the case that the load is not rated to handle these higher voltages, and therefore higher currents as well, that are going to result due to a displaced neutral. Similarly, lower voltages might cause issues insofar that the load is under voltage, meaning that three-phase machines might be underpowered, and single-phase customers or consumers don't receive sufficient supply, that kind of thing. So the displaced neutral can be a big problem because some phases will experience a higher voltage than expected and some will experience a lower voltage than expected. Finally, for this video, let's calculate the phase currents that are going to flow in each of these three phases. We mentioned currents before, so let's work these out because it's thankfully quite easy now because we know the phase voltage across the load or across each load as well as the impedances of each load, and so we can carry this out in a very similar manner to our previous videos where we've calculated phase currents. But in this case we're going to say that I1, the current that flows through Z1, is going to be not V1 over Z1, but it's going to be V1 dash over Z1 because we now know that the voltage across the load is different from the voltage supplied due to this displaced neutral. We know the value of V1 dash and we know the value of Z1. We converted it to polar form earlier when we were calculating admittances as well. So here they are with Z1 in polar form as well. and we get a result of 38.2624 at an angle of minus 4.2493 degrees, and that's a current measured in amps. Here's very similar working for I2, in this case V2 dash over Z2. Again, just converting so that we're consistently in polar form, we can divide to get a result for I2. And here's the same for I3, this time V3 dash over Z3, and we can do those similar divisions in polar form to get our result for I3 as well. Again, we're just sort of hurtling through that for time's sake, but if you want to pause the video and make sure that you can calculate those for yourself, then go ahead and do so. The last thing we'll do, I keep saying the last thing, but the last thing for real this time, the last thing is just a quick check that we can do, because using Kirchhoff's current law, we've got a junction here. If we look back at the original diagram here, we have a junction at which we are determining our neutral, displaced neutral voltage here at the center of the star point. But because of Kirchhoff's current law, we know that whatever currents go into that junction must flow out of that junction. And so what we can do is we can do a little check here on what we've calculated. And what we can say is, according to Kirchhoff's current law, I1 plus I2 plus I3 must be equal to 0. And that's not to say that the current at the star point is 0. That's not true. That's the case for a balanced network. All that we are saying is that the sum of these three currents is 0 according to Kirchhoff's current law in order for the law to hold true. And what we can do is perform this check by just adding our three currents. And what we should hopefully find is that they're equal to 0. In our case, we have these three currents in polar form. We've worked out I1, I2, and I3. Again, we're adding, so it's probably more convenient to convert those to rectangular form in order to add them together. Now, we've done a lot of converting between polar form and rectangular form and back again. So in our case, we get this result here, 0.057 minus J 0.041. And that, unfortunately, is just due to the rounding error of converting back and forth between polar and rectangular forms, which we've kind of done for the sake of ease in this video. But the downside of that is it introduces these rounding errors that sort of compound as we go back and forward between those two forms. But what we can hopefully see is that we've got something that's near enough approximate to 0, and so this check seems to hold valid that we're conserving Kirchhoff's current law here when we get that result. So I hope you found this video useful on an introduction to neutral displacement and how we can apply that using Millman's theorem to calculate the value of our displaced neutral voltage and how that affects our resulting calculations for voltages and currents in an unbalanced star network.